All right, so we are going to pick up from last time. And before I dive in, we're actually going to be starting on R today. And right here, I have a couple lines of code where I have this thing library with a name of what's known as a R package. So when we were learning about packages in the tutorial, in the first two lectures, I did mention how because R is an open source software, other people can contribute to it. And so there are certain external packages that you can install that enable you to use essentially functions and functionality that other folks have built. And so here I'm just loading three fairly common ones. So the first is data table, and then there's a package called Calplot and Ggplot 2. So I'll talk really briefly about these. I'm not going to go into a huge amount of detail, but because I often employ tools coming from these packages, I did want to provide some details. So if you want to learn a little bit more in depth on these, I'm providing a couple websites that I think have fairly decent tutorials on these packages. But I will, whenever we encounter something that's specific to the package, I will sort of go over it briefly. Data table is sort of a functional equivalent to data frames. So these essentially are tables in R, but they're functionally a lot more powerful. So the person who built this really sort of emphasized memory and speed. So using this package allows you to, for example, I can open up a file that is several gigabytes, which if you did it with the default R programming, it would take, it could take on the order of, tens of minutes to load, whereas with data table, it'll load in just a couple seconds. So, little things like that. And then there are specific nuances with the way that you can query things within the table that is definitely a little bit more complex than the base package, but also allows you to do some pretty powerful analysis. And so again, I will briefly mention any time that we're starting to use functionality that's outside of the base R. Okay. So I actually wanted to provide a slightly different example of when we're thinking about standard errors and R squares. And there's actually a very sort of easy way of demonstrating, again, this idea that the standard error and the R squared, which are really sort of commonly used metrics to determine the quality of a model, may not always be sort of the end all be all of these types of metrics. So we're going to repeat the example that we had from last class. And so we're going to leverage the same thing again. So we have in line 12, defining X 100 random draws from a uniform distribution between 0 and 50. And here I'm going to create my random error, which I'm going to draw from a normal distribution with a mean 0 and a standard deviation of 5. And I can write these in just to be a little bit more clear. Mean equals 0, SD equals 5. Go ahead and run that. And same thing from before, we get to create our own true function here. And so in this case, I'm writing data table instead of data frame, but actually the way that it's filled out is essentially exactly the same. So now we'll have a data table, and then we'll just create our model, which is just as a refresher, LM standing for linear model, and I'm going to regress Y on X. And the data that I'm going to be drawing from is for model.1 as we defined in line 15. And so I can run this, and then I can quickly examine the structure of this. And so this is kind of like last time. We know that the true value of X is about is exactly 0.5. Here our estimate based off of the data with random noise is about 0.48. And that is statistically significant. So we're fairly confident that at least the value is doing something or has some kind of measurable relationship with Y. And then the estimate is, we know that for the intercept should be 0, and indeed it's somewhat close. It's not statistically significant. And so, a large proportion of the time, 63% of the time, it's going to be 0 or above. Great. So that is a nice little refresher. And then we had in our, let's see, model 2, which is going to be exactly the same, except that you have double the deviation. So if I do this and multiply by 2, so this was our example 2 from last class. And again, I'm going to just quickly replicate this example. And then run the linear model with Y2 instead of Y1. So Y2, this data is from my second data table. Oh, I didn't run it yet. Okay, whoops. I need to call this Y2. Oh no, what am I doing? There we go. All right. And we can look at the results of this model. And again, similar type of interpretation, right? We know that the true value is about 0.5. This one's a little bit farther. Standard error should be slightly larger, and we can check that. Yeah, it's double, which reflects the fact that the random error term is double the size. Great. So I can show in Ggplot a comparison of these two plots. So I am just going to sort of copy and paste the code over because I'm not going to teach the Ggplot syntax right now. But this is something that if folks are interested in, I'd be happy to cover later. One package that I didn't talk about right at the beginning up here is Calplot. And I just use this because it has this nice little feature that allows me to plot things into a grid. So I can do side-by-side comparisons. So I can show what that looks like. If I run this. Great, okay. So these are two plots. Oop, I think this needs to be Y2. Let's try that again. Yeah, there we go. So if we look at our comparison of our two plots, where we have the first example and the second example, you can see that the spread of the data is quite a bit larger, and it's leading to a larger standard error and therefore sort of larger confidence intervals around our estimate of the fit. Okay, and so here is where we want to demonstrate a sort of interesting artifact of the standard error and the R-squared metrics. And so what I want to do right now is we're going to do a quick review of how you actually derive the standard error. Again, this is actually one of the equations that I wrote that I said you don't need to memorize. But what we want to do right now is to see what happens if we actually manually assign an incorrect beta. And the idea here is that you may in the future run into a solution that might be biased. In other words, we know that there might be something systematically wrong with the coefficient that reflects a difference, like a systematic difference between what the estimate is and what the true value is. And again, because we know what the true value is in this case, we can see what happens if we put in the wrong value, right? And whether or not the standard error and the R-squared are going to reflect the fact that something might be wrong in our estimate. So in order to do that, we have to manually calculate the standard error because we're essentially saying we want it to calculate in the standard error for an incorrect beta. Okay, so just as a quick review, and I'll write this down. So the calculation for this is y minus y hat squared. You sum all the values divided by n minus 2 divided by x minus mean of x squared. And we sum all the values. So this is over I, like so. And then take the square root of that. So all I'm going to do is write a custom function in order to calculate the standard error. And the values that I need are going to be my y's, my x's. And then I'm actually going to need my betas to calculate this because y hat is equal to beta x, right? So your predicted value of y is equal to your beta x plus beta x plus beta naught, which in this case is just 0 because there's no intercept. And so that's why we have these as the inputs. So my numerator is going to be sum of y minus x times beta. So this term is equal to the y hat. And then I'm going to square this value divided by the length of y. And that that is what the big N is. It's essentially the number of points in the data, minus 2. Then we have a denominator, which was the sum of x minus the mean of x squared. And then our output is going to be the square root of the numerator divided by the denominator. Okay, so I can run that. And actually, we can check this. This should work. Let's see. So if I do summary of, what was it called? Example model 1. The standard error is 0.036. And if I use our manual function, hopefully this works, x, y, and we know in this case the estimate is 47965, 965. And you can see 0.03637, so 0.03623. Okay, so fairly close. It's going to be kind of a rounding error due to the fact that I'm not putting in the exact values here. But you can see that the calculation is going to be quite close. Okay, and the second thing that we wanted to look at was the manual R squared. So x, y, beta. And the R squared, again, as a reminder, is equal to 1 minus the sum of y minus y hat squared for all i's divided by the sum of yi minus the mean of y squared. Okay, and again, we're just going to write this into the function. These are my 3 inputs because I have y. I have y hat, which is x times beta. And so I need both my x and my beta as well. Okay. So let's go ahead and do this. So the numerator was a sum of y minus x times beta squared. Denominator is the sum of y minus mean of y squared. And then my final r² output value is going to be 1 minus the numerator divided by the denominator. And I'm going to return the output. Great. So we can again check this. It's 0.6414. So if I go ahead and do this, it'll be X, Y, and then same beta 47965. And in this case, I actually know that it's going to be slightly different because there's a difference in what we would assumed with this having an intercept, whereas in the equation that I set up, it doesn't, but it should be, oops, fairly close unless this happened. Oh, you know what? I I wrote it totally wrong. So let's run this again. It should be manual.r2 xy. There we go. So 47965. Okay. So 0.638, whereas this is 0.64. So very, very close. And again, that's actually having to do with the fact that it's assumed that there's an intercept here. So we knew that it wasn't going to match exactly. But okay, so we've now essentially created these two functions that are going to allow us to calculate the standard error and the r². So what I'm going to do is I'm going to use the model from example 1, modified to calculate SE and r² with an imperfect beta. Okay, so let's take a look. And I'm just going to make up a value. I'm going to say 0.45. And we actually know that the true value is 0.5, right? Because we've created our own function. And I'm also going to calculate the r². But again, here I'm going to replace the true value of beta, which again we know is 0.5, with 0.45. And I'm going to compare that to example 2 with the perfect beta. So, or I shouldn't say perfect, with the true beta value, and calculate standard error and r². Y 0.5, which we know is the true value, and r² xy 2.5. Okay, so I'm going to run all of these guys, and we're going to see what happens. Okay. So again, you know, the kind of reason why I harp on this is that actually I've even had students who've taken the class but have kind of reverted back to this idea that like the quality of the model depends on the standard error and r². And so I kind of designed this example to show why that's not necessarily true. Now, if I were to just kind of look at these values and I see this standard error 0.036 compared to 0.07, the standard error in this case is, you know, about twice as small. And then if I look at the R squared, it's about 0.64, which some will argue is a fairly good R squared, compared to here where the R squared is about 0.27, which most folks might say that it's not the best R squared. And so you may actually be tempted, right, to say that example 1 has kind of a better model than example 2. But we've, and to some, with some respects, that is true in terms of kind of like how close the line is to the points, but it doesn't tell you anything about the sort of true, the measure of our fit against the true value, right? Because in fact, we know that in example 2, which has kind of the worst values for standard error and R squared, where we actually have put in the true beta value, and that ends up with sort of quote unquote worse metrics than example 1, where we know you have the wrong value. And so again, think about what that means in terms of the relative quality of the model and its ability to tell you the sort of truth, right, compared to what these metrics are telling you. All right. So let's go ahead and move on. So far, so we have covered linear models. 1, how to interpret, or sorry, not how to interpret, how to estimate. 2, interpreting beta, so also the standard errors associated with beta. And then we started to scratch the surface a little bit about how good is the model. And so some of that bleeds in from the standard error, but one of the more common metrics that we've talked about, or that most folks use, is thinking about the R squared. And so today we're going to think about a couple other metrics that are also fairly common, probably not so much so as the R squared, but I think are all sort of building upon the toolkit of both diagnostics and quality measurement for the model. And so we're going to talk about residuals, RSE/MSE. So this is the residual standard error and the mean squared error. All right, so we have already sort of talked about residuals, but as a refresher, this is the deviation between observed values and estimated values. So let's take a look at what this, what the residuals look like. So X, Y. Okay. Let's see if I can draw this plot here. So let's say we have these data points and a line through them. Let me actually draw a little bit lower. Okay. So let's say these guys are at point A, point B, and C, and that the distance between these, let's say this is a distance of 2, a distance of 1.5, distance of 3, of 1. So this is negative 1.5 and this is negative 3.5. So I can actually plot the residuals. So this is a very common type of plot where you look at your predicted values of y and you compare them against the residuals. Okay, so let's have A, B, C, which are corresponding to these points here. And so if our residuals, if you have kind of a horizontal line here at 0, and then we're going to have a couple of values below and above in terms of the size of my errors or the size of my residuals. So in A, right, I have 2 values here. I have negative 1.5, so right about here, and I have negative 3.5. So actually, let's say this is negative 3.5 here, so it would look something like this. And then for B, I'm at 2. Oops, I changed the color here. And then for C, I have 1 point at 3 and 1 point at 1. So it's going to be here and say here. So this is essentially what my residual plot for this particular fit looks like. Okay, and so this plot on the left is actually one of the best tools that you have in understanding whether or not your model is biased or not. And so when I say biased, I mean that by looking at the errors, it's actually a really easy way to tell if there's something systematically wrong in the predictions that you're making versus where the real points of y are. And so if you start to see some kind of unique patterns in this particular plot of your y hat versus your residuals, that is a really good indication that there's something wrong with the model. And so let's talk about an example of this. So I'm going to have my y hat against my residuals. So 0. So ideally, what you would want to see from a plot like this is essentially a random cloud of points that are centered around your 0, because what that means, let's actually first show a sort of poor example of this. So you have a cloud of data points, but they are all above 0. In other words, there's a positive error associated with all of those points. Okay, and so think about what that would mean for my x versus my y plot. Like, how could I have generated something that looks like that? Well, if I have a fit line, it means that, right, all of these distances are positive, all positive, which means that in order to generate those errors, all of the points in my data would need to actually be above my fit line. And so, okay, you might say, well, you know, why don't I just look at this chart instead of looking at this chart? And that's a perfectly reasonable way of doing it if you can confine your observation and your model to be in these 2 dimensions, right? So we haven't gotten to sort of multivariate regression yet, because we're mainly talking about y equals, you know, beta x. But you can imagine that if I am now starting to look at multiple variables and so on and so forth, all the way to beta n xn, well, now I've got to look at the relationship of, you know, n number of charts, not to mention any possible sort of correlations between x1s and x2s and x3s that may be even sort of harder to spot. And so that once you start getting to multivariate regression equations and models, it really restricts your ability to directly compare one-on-one relationships. But the beauty of doing it with residuals is that this y hat captures all of the information contained in all of the x's. And therefore, I could look at this one simple plot and be able to tell if there's something wrong with the model, right? And so because of that, it's much more common to look at this left graph as a way of diagnosing whether or not there's systematic error in the model compared to looking at the right-hand graph. So again, you know, as we expand our toolkit, I'm never going to be saying that, you know, one particular type of metric or measure of model goodness is going to be better than everything else. But you can imagine that if I am consistently looking at my standard errors and my R² and my residuals, and then some of the other metrics that I'm going to be talking about in just a moment, that's going to give you much more confidence in your results than, you know, just hanging your hat on, you know, 1 or 2 sorts of metrics. Okay, let's consider one more example. So this particular example focuses on this idea there's something wrong when we observe still randomness, but centered around, but not centered around 0. So let's now think about an example where it is centered around 0, perhaps, but where you might see a non-random pattern in the residuals. And what might that look like? So okay, now let's consider a set of residuals that looks something like this. So in this case, you actually have, roughly the same number of points above and below my 0 line. So the centering seems to be right, but instead of maybe like a random cloud of points, you actually see in this case this pattern where some of the residuals are kind of really negative, going up and following this parabolic curve. Okay, and so what might this look like in the XY graph? If our fit looks like this, we've got a couple negative points, right? So maybe something that looks like this, and then a couple positive points. Okay, wait, I can draw this better, hang on. So something that might look like this. Okay, and so again, this might be intuitively obvious if you just look at the XY plot, but again, that's not something, a feature that may necessarily be available once you start to get to more variables and more complex models, whereas the y hat versus the residuals will always be available to measure essentially across any regression model that you choose to employ. And so again, always worth doing a check against your residuals to see whether or not you've got bias in the model. Okay. So that covers the residuals. And then we can actually leverage the errors that we're seeing in the prediction versus the actual points in order to create some metrics, some alternative metrics to consider sort of in the aggregate, right? And kind of the way that I would generally think of the next two things that we're going to be looking at is when you consider what a residual is, right? It is the difference between the error and your actual, the difference between the actual point and your predicted line. Essentially what you want to do is create a model that can kind of reduce that as much as possible. And so taken in the aggregate, you might think, well, let's figure out some metric that measures the quality of the model based on some aggregate measure of those residuals. And so that's exactly what these next two metrics are. So the residual standard error. So this is the RSE, and this is the standard deviation of residual values. And the way that you can kind of think of this is what is the spread of points about the regression line. All right, and so if I write this out, this is equal to, so here I'm going to provide the equation of the RSE, but again, this isn't something that you'll need to memorize. So 1 over n minus 2, sum of I equals 1 to n of yi minus yi hat squared. And oftentimes you can compare the RSE with the mean value of y. So one of the things that is less handy, I would say, about the RSE, as well as the MSE, which we'll talk about in a second, is the fact that unlike the R squared, which is normalized, right, to be between 0 and 1, the RSE and the MSE both can take values that are dependent on the context of the problem. And so you cannot directly compare a residual standard error in one model versus like a completely different model. You can, however, if you're looking at a couple different models that are measured against the same response variable, so the same y, then it is actually valid to do a comparison of the RSEs, and that will actually tell you, you know, relatively how the models will compare in sort of this context. So I will say the residual standard error is, you know, it's a very well-known metric, but it's actually not so commonly used. Its kind of brother, which we're going to talk about in a second, is for a variety of reasons, ends up being a lot more popular as a metric for doing things like model validation. And so we won't actually use the residual standard error very much in doing model validation.
Can I ask a quick question?
Yep.
So can you talk a little bit more about how we can compare it to y bar? So what are we looking for, I guess, when you're making that comparison? Are we looking like this scale of our residual standard error compared to y bar?
Yes. So when we think about when you think about what the residual standard error is, the size of let's see, where is it? The size of the standard error for any one particular coefficient is actually kind of reflected in this equation, right? This is essentially the numerator part in the calculation for your standard error. And so what that means is that when you compare the spread of the points about the line, if you compare the spread against the points minus the y bar, which would be the denominator of the r squared, you are essentially saying whether or not the spread of the points, the spread of the points about your prediction is really sort of different from the spread about the points from your Y bar. So you're not actually comparing the value of the RSE with the value of the mean Y. You are comparing the spread of the values about your Y bar. And if the RSE values are like smaller than that spread, or if the aggregate value of the RSE is smaller, then you're essentially saying that the model does a better job of reducing the error in your prediction compared to just having a flat line.
Thank you. That makes sense.
Yep. Okay. So the more common metric is the mean squared error. And so this is simply the average of the square of errors. Okay, and so here is the equation. 1 over n, I equals 1 to big N of yi minus yi hat squared. Okay, and so this actually looks pretty similar to the RSE. And this is actually going to be one of the more common metrics that we use to do validation, especially a little bit later on in the course. So it's definitely kind of worth knowing. And I think the properties of this are fairly intuitive, right? So we've talked about why we square them, right? Squaring the errors so that you get the essentially some measure of the absolute value. And it's really critical to have some kind of normalization by dividing by n. Otherwise, you're essentially saying your square error will actually always continue to increase as you put more and more data into it, right? Because it's just gonna sum up all the extra errors that are happening from having more data points compared to your fit. And so by dividing by n, you are now sort of averaging out, okay, what is essentially sort of the average distance of my fit line compared to all of the points. Okay. And I'm going to introduce a concept that we're going to really sort of build on once we start talking about validation, in particular out of sample validation. So let me draw a graph. So I've got my X's and my Y's. Let's put a line through it as a way of sort of demonstrating the the fit. All right, and so we can figure out what the mean squared error is, right? And that is the relative, it is the average of the squared errors of all of these points compared to that line. And that tells us something important about essentially how quote unquote good this particular line is. This is similar to the RSE in that the way that you do a comparison of the metric is against other models looking at your same outcome variable. Again, unlike the R squared, this is not standardized to be between 0 and 1. The MSE is really context dependent, and depending on what data you're using, it can be really different between models looking at like different data sets. Okay, so what I'm actually going to do is, let's suppose that that this red line is trained on a subset of these x's. And so what I'm actually going to do is, let's just suppose that that we take out these two x's. Okay, and so the red line is still, let's suppose that that fit is meant for all of the other x's, and that it was not trained on these two blue dots. So I can actually draw a different fit through these points that is going to do a much better job in terms of my MSE metric compared to this red line. And so I can draw a line that looks like this. And I actually know that the MSE for this line is going to be equal to 0, right? Because I've actually perfectly, I've perfectly matched my prediction to the location of the true values. And you could do the same thing in any sort of number of ways. I could actually even draw some crazy squiggly line, right, that looks something like this. And this also has a mean squared error of 0. And so this is partly where we can see some of the utility and power of this MSE metric, because what you can see is that if I now omit or sort of put back in my my missing points, in other words, my data that I didn't train on, but I know is kind of part of the data set, you can see that there's now actually a fairly sort of different set of errors for each of these points. So actually, I'll draw it in red for that, and then in green might look like that, and then in yellow I actually have a really big error, and the same is happening here with this point, right? And if we reintroduce our testing points, is what I'll call them, into the data set, how does MSE change? And so if I say in training, you could have something where MSE is equal to that, but is smaller, right, than my original. In testing, I actually could find the converse happening, where you might have a situation like this. And so when we look at this plot that I've drawn kind of intuitively, and I look at the red line versus the green line versus the yellow line, you can kind of visually and intuitively think to yourself, oh, okay, that's kind of obvious, right? Like I'm drawing these squiggly lines through all the points, and that's clearly some kind of like overfitting, if you've heard that sort of term before. And so the mean squared error is one of the best ways that we have to examine whether or not overfitting is happening. And then we're going to be sort of really leveraging that power in validating our models in the future using this concept that I'm kind of laying out right now. Okay, and so keep the sort of principles of the MSE in mind, sort of much more so than just kind of memorizing the equation, because again, this is going to be a pretty important topic moving forward. Okay. The final metric that I'm going to talk about today, another sort of common one that's used, is called the F statistic. It's always kind of weird to introduce the F statistic at this point in the course, because it actually applies mostly to multivariate regressions. But the idea is very similar to the standard error. And so in the standard error, when we're again sort of going back to last class, thinking about what that means, it is this hypothesis that the beta that we're looking at is different from 0, right? If it is statistically significant, that means that we think that a certain percentage of the time, a small percentage of the time, will the beta actually be, essentially equal to 0. And so we're statistically confident that it is different and that there is kind of a measurable relationship between X and Y. So the F statistic is the exact analogy of that, except instead of saying the hypothesis that, this one particular variable has a relationship, the hypothesis is that all betas are equal to 0 instead of a single beta. So it is this measurement of whether or not we think the entire model itself has some kind of statistically significant effect. Okay, and so I'll write the equation. It's a little bit more complex, but again, this is not something that you have to memorize, but I will write out for your reference. Oh, sorry, I am making a mistake here. So this is actually K. And K refers to the number of parameters. So K is number of parameters, or in other words, x's slash betas. So how many x's do you have? Divided by yeah, and we're working in slightly more dimensions here, right? Because you have both the sort of number of data points versus the number of parameters in the model. Okay, and so I don't want to sort of belabor any of the statistical details here, other than to say that this is going to be particularly relevant when we think about something like model selection. In other words, once we get to multivariate models, we're going to be talking about, oh, how do I know whether to include, you know, x1 and x2 or x1 and x3 in sort of different combinations? The F statistic ends up being a sort of useful metric for helping to figure out which variables to put into the model. And the primary reason why I'm including it right now is, you know, we're kind of going over the sort of field of commonly used metrics for essentially how good overall the model is. Okay, and so we've talked about the R squared. We've talked about looking at the residuals as a whole in some of the residual plots. And then we've talked about the residuals, the residual standard error, as well as the mean squared error and the F statistic. And so I think that this kind of covers the broad set of metrics that folks commonly use in sort of diagnosing how good their model is at a high level. All right. So why don't we take a quick break at this point before we sort of jump into some of the application in R. So let's say, let's just say like 4 minutes. All right, let's continue onwards. So hopping back onto the discussion about residuals um, and generating residual plots in R. So we will need to know how to generate the predictions, in other words, the y-hats. And so what that really is actually, we've created this line that fits through these data points, which represents our model. And essentially the y-hats are going to be the point on the line correspond to each point in the data. And there's actually a pretty simple way of doing that. If I simply write predict, so this is a function that takes in the model that we saved, so the example model 1, and this in itself will generate all of the points that correspond to each of the data points in our example. So these 100 points correspond directly as predictions to predictions to my y here. So it's going to be what the model is predicting y is for each of these x's. So that's how we get the y hat. And in fact, you could also feed in new points that aren't actually from that data and see how it predicts based off of your model. And so the way that you would do that is, let's say I wanted to introduce new X data, and I'm just going to say make 4 random points here, 25, 29, 42, 57. We'll do that. And I can predict example model 1, new, so new data is equal to new.x. So it's saying I'm going to put in a new table that contains a column x, which is one of the explanatory variables in the model, and tell me what the prediction is going to be for those 4 points. So these 4 points here are going to correspond to the points along my line here. So at x equals 25, that's going to be y is about a little bit larger than 10. Okay, great. That's what we saw. Let's say if it's at 42 over here, that's going to be pretty close to 20-ish. So that'll be 19.7. Okay, so it's basically telling us where on the blue line we are, right? Which is our y hat. One sort of word of caution about estimating out of bounds. And so one of the things that you'll note is that when we drew our data, we went from 0 to 50. And you can see, in fact, here, our axis goes from 0 to 50. Except that the data point here is at 57. And so that's kind of well beyond where we've calibrated the model. And that's kind of just a general word of caution. You don't want to extrapolate your predictions beyond what you should be capable of doing. Okay. And so I'm going to add, so if I look at my original data, it looks something like this. My X's and my Y's. These are randomly generated, and then the Y's are calculated based off the X plus random noise. And so let's say I want to add an extra column of Y hat for my predicted Y. So I'm going to do it using a method from that's inherent to the data table package, and I'll show the sort of equivalent of that in base R. So this is in data tables. The way that you create a new column can be done as follows. And so this part of it is just what we were talking about in line 60, where we're generating the predictions from our first model. And this colon equals is essentially like the arrow sign. It's an assignment operator. And if I do this, you'll see the predicted values here. Okay, so in default data frame, the way that you would do this is I would create a column called, okay, wait, and this is exactly analogous to above. It would be predict example.model1. Okay. And part of the reason why I'm kind of showing this version, again, it's something that I'm a little bit more used to at this point, but also as an introduction, especially given, if there are any folks interested in working in sort of really big data, I will just quickly comment that this version within data tables is actually much more efficient and a lot faster. And I have run into these problems before, sort of doing it this way on really large data sets, and it could take hours to run, whereas this can run equivalent under certain types of circumstances, within a couple seconds or a couple of minutes. So it's usually hundreds, if not thousands of times faster. But when we're doing kind of small things like this, you won't notice any difference in operation between these two ways of creating a new column. All right. So I'm going to plot this. And what I'm plotting right now is the predicted Y value, so Y hat, compared to the actual Y values. Okay, and I'm going to draw a line with a slope of 1, and we'll talk about what that means in just a second. All right. So when I compare my predicted Y, so my Y hat versus my Y, if my model were sort of perfectly on going through all of the data points, then all of the points here would lie on top of this line, right? Which is, in other words, basically to say that my predicted values match my my actual values exactly. But we know that that's not the case, and that there is, in fact, some error. And so now we're going to figure out how to kind of look at that. So we've done half of the sort of plotting that we want for doing for essentially looking at the predicted y hat or the y hat, in other words, the predicted y values compared to the residuals. So we have the y hats, and so now we need to look at the residuals, which is actually done in a pretty similar way with resid, which stands for residuals. So instead of doing the predict, which gives you the y hat, you just use this function, which will give you my errors. So these are the 100 errors associated with each of the points. And these represent the difference between each particular point and then the corresponding predicted value. So I'll use a default plotting method instead of the Ggplot version here. So I don't think I've really sort of formally talked about any of the plotting approaches. Oops, I'm getting a phone call. Okay, sorry about that. So most of what I've shown in previous lectures have been using the base plot, which is this. The Ggplot is actually a much more powerful tool that enables us to do more complex graphing procedures. And again, that's something that I'll try and show at the end of some classes if we have time. But in the base version, the syntax is actually, I think, a lot sort of easier or initially intuitive than Ggplot. So we just have our x values, our y values, and then these are just the way that you label the axes. So x lab and y lab. So let's take a look at what this looks like. I'll kind of expand this. So here are the residuals. And yeah, I think that, it's this sort of cloud of points. You can't really see too much of a pattern going on. You might argue that there's some kind of like curve going here, but I think generally this looks fairly good in terms of a residual plot. I would be kind of happy to say that it's unlikely that there's going to be some systematic bias, at least that I'm seeing from this set of residuals. Great. Okay. And so this is, yeah, so this is essentially the way that that you would want to employ the metric of residuals. Is by kind of qualitatively and visually kind of looking at the spread of residuals compared to your predicted y values. All right. Since we actually have a little bit of time here, I thought it might be interesting to actually talk about some of the Ggplot examples of things that you could do. since I'm introducing it in this lecture. So I guess for the few folks who are here, maybe I'll pause for a moment before I sort of jump into talking about Ggplot and just see if there are any immediate questions. And if not, then we can move on.
None from me.
Okay. Great. Okay. So I'm going to actually be drawing on a couple sort of data sets that I'm going to make available onto Canvas after this. So right now, you're actually not going to be able to code along, but that's okay. It'll be better to maybe just sort of follow along with what's happening here. So I am actually going to use a data set on the coronavirus as our example for sort of data visualization. Okay, it is because I am not in the right directory again. So let's quickly change that. So Dropbox. All right, let's try that again. Okay, and so
question.
Oh, yeah, go ahead.
Sorry, I was just curious, how is this read call?
Yeah.
Like why is that one used?
Yep. Excellent question. So actually, let's take a look here. Okay, I guess that's not quite big enough to make a difference. So the base version would look something like this. There's a couple different ways I could read this. Coronavirus, and these are all, again, functionally equivalent. Read.csv, data, coronavirus. So this is base R's version of reading in a comma separated value file. And actually read.csv is actually just a wrapper in base R for read table. And you can see this reads in any sort of generic file. And the thing that distinguishes the CSVs is that the limiter, the separator, is a comma. So these are all functionally equivalent. So it would look something like this. And so the read table is the generic version of CSV, where you're allowed to do other sorts of separators. And what I have here, this is data table version for loading data. And when you load in data, it'll automatically load it as a data table. And this is definitely one of the most handy functions that I've learned about compared to this. And I sure do wish that I knew about this in grad school, because I actually used to load, when I was in grad school, I would work on these large registration data sets. And doing anything, manipulating the data was always a pain because it literally took 6 hours to load the data onto a computer or onto R. And so, you know, there would be days where I would like, you know, let it load overnight just so that I could work with it in the morning. And actually, I learned about FRead later on, went back and loaded the data, and it took about 30 seconds to do. So this is another one of the examples of the really extreme efficiency of the data table package for manipulating large data sets. Yeah, so this particular data is not huge, but even for something like this, I'm almost certain you would see like you would see a noticeable difference in the load time between the data table and the base version. And I say noticeable, not in terms of like human time, because actually it would probably be you know, not noticeable. But if you actually measured it with the like internal timer, it would probably be like 10 to 100 times faster.
So is there any disadvantage to just using this one as the default? That's
Nope.
like your personal default? Okay.
Yeah.
Good to know.
The only disadvantage is that you have to load in the data table library to do that. But other than that, there is not really any disadvantage. And I'll also say I don't actually recall if this is something that I've talked about before, but there are kind of two competing big data packages. So the kind of different, I think it's kind of like different schools of thought, not really schools of thought, it's just different people use data table versus dplyr. And dplyr is actually, I think, a lot more popular because it's part of this larger set of packages that a lot of data scientists use called tidyverse. And so that's something that you can look into if you're interested in. And there's an argument that dplyr is I guess easier to understand because of the way they do this thing called piping. But I sort of learned about data tables first, and so I'm sort of much more versed in that versus dplyr. And I will actually really quickly provide a link. This is kind of a handy tutorial that if you want to learn about data tables or dplyr, this is handy. But they actually have this thing where on the left-hand side, they do some examples in data table, and then on the right-hand side, they do the exact same examples in dplyr. So you can see the sort of comparative approaches that you would employ using each of these two packages. And so I know the left-hand side very well and the right-hand side kind of less well, but I can always jump into this tutorial to see how things are done on sort of both ends. And so I will make sure to include this here. Comparison tutorial. Okay.
Quick question, Alan.
Yeah, go ahead.
I'm curious if can FRead also handle all types of data like characters, or do we need to clean up or do any operations afterwards?
Yeah, so functionally, it's going to do the same thing as read CSV or read table. And so in terms of like cleaning data, like it will read in like dirty data, and then you could then clean it afterwards in R. But yeah, it doesn't have like a problem with reading any particular data types.
And it's part of the data table library, if read.
Yep, exactly.
Yeah. Thank you.
Okay, so I'm including a couple other lines of code here. Don't worry about this. This is just doing a little bit of cleaning. And then I'm also going to load in some census data. Okay, so let's just take a look at this data and see what's included. So essentially, this is a breakdown of coronavirus cases. And so this is, there are 8 columns. You've got a date column, county location, state location. FIPS is essentially a standard index for a particular type of location. And so you can actually see the breakdown. 53061 is the combination of the state and the county. And so the state designator is here, 53, referring to Washington. You can see down here, like 56 refers to Wyoming. And then the county 61 is Snohomish, and you can see how it's kind of combined into this. And then we've actually got the metrics of interest. So the number of cases and the number of deaths. I actually kind of stumbled across this data set last year during when I was teaching this class as well. And so it was really interesting kind of coming back to it and sort of reloading all of the updated data and seeing how all the sort of plots have changed from the examples that I was doing last year. Okay, so let's then look at the other table that we loaded, which is the census table. Okay, so this is way bigger. Let's actually look at it in here. Okay, in the viewer, we can see a whole bunch of different metrics. And so I think the main one that we'll kind of really be thinking about are going to be like the population estimates. Yeah. As well as, I have something else here, natural wind. Okay, yeah. So I'm also going to grab this column, natural, I think this is actually income, but we'll check that in a second. Okay, and so what I'm actually going to do is to merge my 2 data sets, my coronavirus and my census data sets. And then I'm not going to grab all of the data from the census. I'm just going to grab a couple of these columns. So state, county, population estimate. And then if you remember from last time, we are doing an intersection, right? So we want to do overlapping columns. And so both of the data sets contain information about the state and the county. And so it's actually using the FIPS code for the state and the county, which is what you can see here in the census data set, state and county. These are the FIPS numbers that refer to both of those. And so I can go ahead and merge this. And we should now have case, we should essentially have all the matches of the state and county alongside sort of the number of cases and deaths, as well as the population estimates and income. So we do notice that there are some missing data where the match wasn't able to successfully do this, successfully merge. And so I'm gonna just, in this case, ignore that data. So we're gonna drop it. So the way that I do that is using a function called complete cases, which basically will look at each of the rows and say, hey, is there any missing data here? And if there is, I'm just going to return false. And so for that corresponding row, when I return it, it will drop it. So if we do this, so we'll go from 1,173,000 observations down to 1,135,000. So still sort of more than enough. And again, this particular exercise is just kind of to do, it is kind of to just do some visualizations. So this is kind of like my first bit of data cleaning that I'm doing. There is a couple other things that I will want to do. If I look at the structure of the data, I will see that, you know, I've got some integers, some characters, some more integers. But actually the date, there's actually a specific date type that you can use. So we'll go ahead and convert that. So this is using the data table type of syntax to create or to modify a column. So all I'm going to do is this command, which will convert all of the dates. And we should be able to see that when I look at the structure again. Now the date has a date format, which is convenient for doing graphs. I can do something like look at new cases. So again, I think some of this syntax is going to be newly introduced, but hopefully you can see kind of what's going on here. So cases are cumulative cases, and so if I want to do the new cases, I have to take my cases and subtract from the old cases. Okay. So this is where you get to some of the like real power behind data tables, is that it can do operations by groups. And so you want to do the shift of cases by each of the locations. And you can kind of start to imagine where the programmatic aspect of cleaning data becomes really powerful, or sort of modifying the data. If you think about how you might try and do a procedure like this in something like Excel, it's definitely doable, but it's very it would be a lot more involved than kind of just doing it in sort of this one line of code. Okay, and so I'll run this. And so now I can see, for example, the new cases sort of every day as I move on through time in each sort of location. Okay, and let's suppose so actually I'm going to kind of breeze through this and maybe just explain what the code is doing. Here I'm creating a different table where I can look at a specific breakdowns by county. And in this case, yeah, in this particular case, we can essentially group the total cases, right, by sum. So if I add up all of the new cases, and if I look at what's the sort of largest set of new cases broken down for each of the locations, we can see what that looks like. Okay, so what I will do is start to plot this. And so what I want to look at is, let's say, the log of my population compared to the number of cases. So let's just quickly look at what that looks like. So I think here what I'll do is try and showcase some of the power of this particular plotting package called Ggplot. This I think will be more kind of as a showcase because I understand that like I'm probably moving through the code fairly quickly here. And so let's sort of more treat this as a way of kind of showing what this can do. So this is kind of the first step, and we're going to start to layer in more complexity. So this you would be able to do fairly easily in the base plotting package for R. And all this looks at is whether or not there's some kind of relationship between the total number of cases that we're observing in coronavirus versus the population of different counties in the country. And so, okay, well, you might say, well, you know, is there anything particular about, you know, specific states, for example, where the trend might be different, or if there's some kind of systematic difference between counties in one state versus another, where the relationship between the population and the number of cases of coronavirus might be different. And in fact, we could really easily kind of break out what would it look like for each individual state. And so I'm going to show you how to do that here. You have this extra add-on facet, which essentially is going to separate out into groups all of these by state. Okay, so you can see, well, that's quite a lot of states. Maybe it's a little bit harder to kind of see exactly what's going on. So why don't we kind of look at a couple specific states. So let's say California, New York, and Michigan, Texas, a couple of the big states, right? So let's try that again. Okay, cool. And so you can see one of the sort of unique features about the Ggplot is that it can really quickly take advantage of the way that the data is set up to kind of manipulate the visualization in different ways very easily. If you were to do this in the base plotting package, you'd essentially have to like separate out the data and then call the data in certain ways. Whereas I can do this like very easily with essentially like one sort of line of code. Okay, so I think I'll continue maybe coming back to this example and doing a couple more like showcase elements, and I'll encourage folks who are like interested in the sort of Ggplot visualization power to check out the tutorial to sort of get your hands on it. And I think a really good way of like learning this is just to employ it like in practice. So if you are interested in taking some time to learn Ggplot, do it on the homeworks. Okay, and I guess we're just about at time. So I will end here today. And again, we may pick up on this particular data set and looking at other visualizations whenever we have a little bit of time in class. Yeah, and so thanks everyone for bearing with having to watch a pre-recorded lecture. And otherwise, yeah, I guess I will see you all next week.